Hello, and welcome to Late Night Physics. I'm thrilled to have you here as we dive into some of the deepest, most fascinating questions about the universe. Before we begin, don't forget to like and subscribe so you never miss out on any of our mind-bending explorations. And while you're at it, drop a comment below letting me know where you're watching or listening from. It's always interesting to see where in the world, or perhaps beyond, our curiosity about the cosmos reaches. Now let's get comfortable, because tonight, we're going to embark on an extraordinary journey into the fabric of reality itself. We'll be unraveling the mysteries of time, gravity, and the very nature of what is real. From the way space and time are woven together into something called space-time, to how gravity isn't just a force but a curve in the very fabric of the universe. Prepare for a tour through the heart of general relativity, and perhaps beyond. Whether you're joining us from Earth, or maybe even imagining a distant future where we're contemplating the universe from the comfort of some new planet, this journey is for the curious minds who dare to ask, what if the way we understand time, gravity, and reality isn't quite the way it really is? So sit back, relax, and let's explore how the universe operates on the grandest scales, shaping the very essence of who we are and where we might be going. Let's begin. Space, time, and gravity. These three concepts form the foundation of how we understand our universe. They are the invisible threads that weave together everything we experience, from the motion of the stars to the ticking of the clock on our wall. But despite their significance, these ideas were not always as clear as they are now. For centuries, the great minds of the scientific world believed that space and time were fixed and unchanging. Time was something that marched forward, steady and reliable, while space was a stage where events unfolded, with no real connection to time itself. Gravity was seen as a force, a mysterious pull between masses that acted instantaneously over vast distances as though it knew no bounds. Then, in the early 20th century, a shift began to take place. The ideas that had governed science for centuries, ideas that were rooted in the works of Isaac Newton, were being questioned and in some cases upended entirely. The catalyst for this change was a man named Albert Einstein, whose theory of relativity transformed our understanding of space, time, and gravity forever. But Einstein wasn't working in a vacuum. The story of relativity is not just the tale of one man, but of a larger intellectual revolution that was brewing in Europe. Before Einstein's work, there were others, lesser-known thinkers who helped lay the groundwork for what would become one of the most important breakthroughs in the history of science. One such thinker was Henri Poincaré, a French mathematician and physicist who was already thinking in ways that would resonate with Einstein's later discoveries. Poincaré recognized that time might not be as absolute as people once thought. He understood that our perception of time could change depending on how fast we were moving, a realization that foreshadowed Einstein's ideas of time dilation. But Poincaré didn't go as far as Einstein did in formulating a full theory of relativity. Nevertheless, his work was instrumental in the intellectual environment that led to Einstein's revolutionary ideas. In fact, Einstein's theory of special relativity, which he published in 1905, relied on an idea that had been hinted at by many of his predecessors, that the laws of physics should work the same way for everyone, no matter how fast they are moving. This was a radical departure from Newtonian mechanics, where the laws of motion applied differently depending on the observer's position or velocity. With his special relativity, Einstein proposed that space and time were not fixed backgrounds upon which events took place, but were instead flexible and could change based on the observer's motion. This flexibility in space and time would become even more apparent in Einstein's later work, when he developed his theory of general relativity, published in 1915. General relativity went even further, proposing that gravity wasn't a mysterious force acting at a distance, as Newton had suggested, but was instead a result of the curvature of space-time itself. In other words, massive objects like planets and stars cause space-time to curve, and this curvature was what we felt as gravity. Imagine a heavy ball placed on a stretched-out rubber sheet. The ball causes the sheet to sag, and anything near the ball is pulled towards it. In the universe, the sun acts like that heavy ball, bending space-time and causing the Earth to orbit around it. But this wasn't just a theoretical idea, it could be tested. One of the first pieces of evidence came in the form of a simple observation, the bending of light. In 1920, an expedition led by British astronomer Arthur Eddington observed a solar eclipse and measured how light from stars was bent as it passed near the sun. The results confirmed Einstein's predictions, proving that mass could bend space-time just as he had said. For Einstein, space and time were no longer separate, but were deeply interconnected in a four-dimensional fabric known as space-time. This is where the magic happens. Space-time isn't just a passive stage on which events unfold, it's active, dynamic, and shaped by the presence of mass and energy. And the geometry of space-time governs how things move. This was the brilliance of Einstein's general relativity. It gave us the first clear understanding of how gravity works, not as a force between objects, but as a warping of the very fabric of the universe itself. It's hard to overstate just how revolutionary this was. For the first time in history, scientists had a theory that not only described the motion of planets and stars, but also provided insight into the very structure of the universe. The notion of space-time as a single, flexible entity made the universe seem like a much stranger place than anyone had ever imagined. And yet, as we dive deeper into this strange new world of relativity, it's important to remember that Einstein's work didn't emerge out of nowhere. It was part of an ongoing intellectual evolution that stretched back for centuries, from the early ideas of thinkers like Galileo, who challenged the idea that the Earth was the centre of the universe, to the work of Isaac Newton, whose laws of motion and universal gravitation set the foundation for much of modern physics. The journey to relativity was one of gradual discovery. Each new step in the journey built upon the knowledge of the past, and Einstein's brilliance lay in recognizing how the ideas of his predecessors could be woven together into something entirely new. But the story doesn't end there. Once Einstein showed us how space and time were connected, a new question arose. How could we understand this strange new fabric of space-time in even greater detail? What would happen if we pushed Einstein's theory to its extremes? Could space-time itself be warped so much that light couldn't escape, creating what we now know as a black hole? And what about time itself? Could it stretch and twist in ways we don't fully understand yet? These are the questions that will lead us into the next stages of our journey, where we explore the ways in which space-time can bend, stretch, and reveal some of the most bizarre and fascinating features of our universe. The universe, as it turns out, is much more flexible and strange than we ever thought possible, and we're just beginning to understand its true nature. Imagine, for a moment, that you're standing at the edge of the universe, looking out over everything that exists, every planet, every star, every galaxy. What do you see? The vast expanse of space stretching out in every direction, right? But what if space itself isn't simply an empty void? What if it's something far more dynamic, far more complex than we ever imagined? This is where the concept of space-time comes into play. Space-time is a term that at first may sound a bit abstract. After all, we're used to thinking of space and time as separate things. Space is where objects exist, and time is how we measure the passage of events. But what if these two are not separate at all? What if they're part of a single, unified fabric that weaves together everything in the universe? This is exactly what space-time is. A four-dimensional framework where the three dimensions of space, length, width, and height, are combined with the fourth dimension of time. It's like a giant cosmic grid that extends not just through space, but through time as well. The idea of space-time wasn't always so clear. For a long time, scientists thought of space as an unchanging stage, a backdrop upon which events occurred, and time as a constant, moving forward at the same pace for everyone. This view began to change, though, as new ideas started to emerge. One of the most important contributions to our understanding of space-time came from a French mathematician and physicist named Henri Poincaré. Poincaré was an incredibly influential thinker, and while he is often overshadowed by the more famous Einstein, his work set the stage for many of the breakthroughs that would follow. Poincaré realized that time wasn't necessarily the same for everyone. He saw that time could change depending on how fast you were moving, a concept that, while subtle, would eventually lead to Einstein's theory of relativity. Poincaré wasn't alone in this insight. Other thinkers were also beginning to explore similar ideas, yet it was Einstein who would put it all together in a way that would forever change how we see the universe. In the year 1905, Einstein published his theory of special relativity, which fundamentally altered our understanding of space and time. The key idea was this: space and time are not absolute, they're not fixed and unchanging. Instead, they're intertwined, and they can stretch and compress depending on how fast you're moving and how much mass or energy is present. Einstein's theory suggested that the laws of physics should be the same for everyone, no matter how fast they're moving. But more than that, it showed that the speed of light, unlike anything else, is always the same, no matter what. This insight changed everything. It meant that space and time were not two separate entities, but were part of a single, unified framework: space-time. Imagine, for a moment, that you are moving through space at a very high speed. According to Einstein, your experience of time would slow down compared to someone who is standing still. This is what we call time dilation, and it's a direct consequence of the fact that space and time are interconnected. But the story of space-time doesn't end with Einstein. Another key figure in understanding the nature of space-time was Hermann Minkowski, a German mathematician who took Einstein's theory a step further. In the year 1908, Minkowski realized that it was possible to describe space-time geometrically, using the same kind of mathematics used to describe shapes and curves. He saw that, just like a flat sheet of paper can be curved into a cylinder or a sphere, space-time itself could be curved and shaped. This was a breakthrough idea, as it allowed scientists to visualize space-time as a kind of fabric that could be bent, stretched, and distorted by the presence of mass and energy. In fact, Minkowski's work laid the foundation for what would later become Einstein's general theory of relativity. So, what happens when space-time is curved? This brings us to Einstein's field equations, which are the heart of general relativity. These equations describe how mass and energy warp space-time, and how that curvature influences the motion of objects. At its core, the field equation is simple. It relates the geometry of space-time to the distribution of matter and energy. It's a bit like saying, the way the universe is shaped depends on what's in it. If there's a lot of mass like a planet or a star, space-time curves more strongly. If there's less mass, the curvature is weaker. This is why planets orbit the Sun. The Sun causes space-time to curve and the planets move along the curves in that space-time. Einstein's equations also predict some truly strange phenomena, like black holes, where space-time is curved so much that nothing, not even light, can escape, or gravitational waves, ripples in space-time caused by massive objects accelerating, like two black holes merging. These waves were first detected in 2015 by the LIGO collaboration, providing more evidence for Einstein's theories and opening a whole new way to observe the universe. But even as Einstein's theory of relativity became well established, other thinkers began to explore the nature of space-time from a different perspective. One such thinker was David Bohm, a physicist known for his work on quantum mechanics. Bohm proposed ideas that challenged the way we think about space-time. He suggested that the universe might be deeply interconnected, not just through space and time, but through something he called the implicate order. This idea suggested that everything in the universe is interconnected in ways that go beyond our ordinary perception of space and time. While this theory is speculative, it points to a deeper, more fundamental way that space-time and reality might be connected, one that science is only beginning to explore. As we move forward in our understanding of space-time, it's important to remember that while general relativity has been incredibly successful in describing the large-scale structure of the universe, there's still much we don't know. For example, while we can describe the curvature of space-time around massive objects, we don't yet fully understand how this fits with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. The search for a theory of quantum gravity, which would unite general relativity and quantum mechanics, is one of the biggest challenges in modern physics. But for now, we can marvel at the beauty and elegance of Einstein's theory, which has revolutionized our understanding of the cosmos. Space-time, the unified fabric of the universe, isn't just a passive stage where events unfold, it's an active, dynamic player in the grand drama of the cosmos. The more we learn about space-time, the more we realize just how strange and fascinating the universe truly is, and the journey's just beginning. One of the most fascinating aspects of Einstein's theory of general relativity is the way it fundamentally changed our understanding of how mass and energy interact with the fabric of space-time. Before Einstein, scientists understood gravity as a force that acted at a distance, something like an invisible rope that pulled objects toward each other. But Einstein's insight was something far more profound. He showed that gravity isn't a force at all in the traditional sense. Instead, it is the result of the curvature of space-time caused by mass and energy. To understand this, imagine space-time as a stretchy fabric. When a massive object, like a planet or a star, sits on that fabric, It causes the fabric to bend and curve. The more massive the object, the more it warps the fabric. Smaller objects like moons or satellites then move along the curves in this fabric. In this way, gravity is not a force pulling them directly, but rather a consequence of the way space-time itself is shaped. The Earth orbits the Sun not because the Sun is pulling on it, but because the Sun's mass causes space-time to curve, and the Earth follows the curved path laid out by that curvature. Einstein's general theory of relativity, published in 1915, gave us the mathematical framework to describe this warping of space-time in precise terms. His field equations, which relate the distribution of mass and energy to the curvature of space-time, are the heart of the theory. They tell us how space-time curves in response to the presence of mass and energy. In their simplest form, they are expressed as g equals 8 pi t, where g represents the curvature of space-time, and t is the energy and momentum of the matter within that space-time. Though the equations are mathematically complex, their basic principle is simple. Mass and energy warp space-time, and that warping is what we perceive as gravity. But as revolutionary as Einstein's work was, it wasn't done in isolation. There were others who contributed to the development of ideas surrounding space-time, mass, and energy. One such figure was John Archibald Wheeler, a physicist who played a major role in advancing the study of black holes and the dynamics of space-time. Wheeler famously coined the term black hole to describe regions of space-time where the curvature is so extreme that not even light can escape. But Wheeler's ideas didn't stop there. He also proposed that space-time itself might be more dynamic than we think, and that it could be affected not just by the presence of mass, but by the way mass behaves. Wheeler's work on black holes was particularly groundbreaking. He demonstrated that when a star collapses under its own gravity, it can form a black hole, an object with an infinitely small, infinitely dense point at its center called a singularity. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. The idea of black holes was anathema to many physicists at the time, as it seemed to violate the fundamental principles of physics. But over time, Einstein's equations began to provide clear evidence that such objects could exist, and today, black holes are a well-established part of our understanding of the universe. Wheeler's insights helped to push the boundaries of how we think about space-time, but the story doesn't end there. Another scientist who expanded our understanding of space-time's flexibility was Kip Thorne, a physicist best known for his work on gravitational waves and wormholes. Thorne proposed that space-time could not only bend, but could also stretch and twist in extreme ways. One of his most exciting ideas was the concept of wormholes, tunnels in space-time that connect distant points in the universe. If such a wormhole could be stabilized, it might allow for faster-than-light travel, potentially enabling journeys across vast distances in a fraction of the time. Wormholes are theoretical, of course, and we don't yet know if they exist. But they are a natural consequence of Einstein's equations, and scientists like Thorne have spent decades exploring their potential. The idea of a wormhole is intriguing because it suggests that space-time, despite its seeming rigidity, could be much more flexible than we ever imagined. Space-time isn't just a passive, unchanging stage on which events occur. It is an active, dynamic entity that can twist, stretch, and curve in ways that defy our intuition. Thorne's work on gravitational waves is another example of how space-time can reveal its mysterious nature. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as when two black holes merge. These waves were predicted by Einstein in 1915, but it wasn't until 2015 that the LIGO collaboration detected them for the first time, confirming Einstein's predictions. The detection of gravitational waves has opened up a new way to observe the universe, allowing us to hear the most violent and energetic events in space, like the collision of black holes. While Einstein's equations give us a clear picture of how mass and energy influence the curvature of space-time, they don't provide a full understanding of the quantum world. This is where theories like those proposed by Lee Smolin come into play. Smolin, a theoretical physicist, has suggested that space-time itself might have a more fundamental, granular structure than we currently understand. In his theory of quantum gravity, he posits that space-time could be made up of discrete building blocks, like a network of tiny, interconnected loops. This idea, known as spin networks, takes us into the realm of quantum mechanics, where particles behave in ways that defy classical expectations. According to Smolin, Space-time could be emergent from these quantum interactions, rather than being a smooth, continuous fabric. If this theory is correct, it would radically change the way we think about space-time. Instead of viewing it as a smooth, continuous backdrop, we would see it as a dynamic, granular structure that evolves over time. This would also solve some of the puzzles that arise when we try to combine general relativity with quantum mechanics, two theories that currently seem incompatible in certain situations. Smolin's work is still speculative, but it pushes the boundaries of what we know about the universe and opens up exciting possibilities for the future of physics. As we dive deeper into the nature of space-time, mass, and energy, we begin to see that the universe is far more complex and interconnected than we ever realized. Einstein's theory of general relativity gave us the tools to understand how mass and energy warp space-time, but it also raised new questions. Questions about the very nature of gravity, the behavior of black holes, and the potential for phenomena like wormholes and gravitational waves. These ideas stretch our imaginations and challenge our most fundamental assumptions about the universe. The curvature of space-time is not just something we see in the movements of planets or the bending of light. It is the very fabric of reality itself. The more we learn about how mass and energy shape space-time, the more we begin to appreciate the interconnectedness of everything in the cosmos. But there's still so much we don't know. The next chapter will take us further into the strange, twisted world of space-time, where time itself can be affected by the curvature of space, leading to some of the most mind-boggling consequences of general relativity. Imagine for a moment that you could slow down time. What would that be like? Would it feel as though the world around you is moving faster while you remain still? Well, in the strange world of relativity, this isn't just a thought experiment, it's a reality, one that's deeply tied to how gravity and motion affect the passage of time itself. In Einstein's theory of relativity, time is not a universal constant that ticks away at the same rate for everyone, everywhere. Instead, time is something that can stretch and contract depending on your speed and the gravitational field you're in. This phenomenon is called time dilation, and it's one of the most mind-bending consequences of relativity. Time dilation happens in two different ways, due to motion and due to gravity. First, let's look at motion. According to Einstein's special theory of relativity, the faster you move relative to someone else, the slower time passes for you, at least from their point of view. This effect becomes more pronounced as you approach the speed of light. So, if you were travelling in a spaceship at near-light speeds, time for you would pass much more slowly compared to someone who is standing still on Earth. This is where the famous twins paradox comes into play. Imagine two twins. One stays on Earth, and the other takes off on a space journey at nearly the speed of light. When the travelling twin returns, they'll find that their sibling on Earth has aged far more than they have. To the travelling twin, only a short time has passed. Meanwhile, years or even decades have gone by for their twin on Earth. The paradox is called a paradox because at first glance, it seems like each twin should think the other has aged less. But relativity makes it clear that the twin who travels at high speed experiences time more slowly due to their motion. This strange effect has been confirmed in experiments using precise atomic clocks, showing that time really does pass differently depending on how fast you're moving. But time dilation doesn't only happen because of motion. Gravity also plays a role in how time flows. According to Einstein's general theory of relativity, the stronger the gravitational field you're in, the slower time passes for you. This means that time passes more slowly on the surface of Earth than it does in deep space, far from any massive object. If you were to spend some time near a black hole, where gravity is extremely strong, you would experience time at a dramatically different rate compared to someone who's far away from any massive object. This is called gravitational time dilation, and it's been observed in real experiments, like when scientists measure the difference in time between atomic clocks on the ground and those in orbit on satellites. The clocks in orbit tick a little faster than the ones on the ground, because the Earth's gravity is weaker the higher you go. Now, time dilation raises a really interesting question. If time can stretch and shrink depending on how fast you're moving or where you are in a gravitational field, can we somehow use this to travel through time? Can we harness the power of relativity to travel into the future, or even the past? This is where some of the more speculative ideas in physics come into play. One of the most intriguing concepts comes from a physicist named Miguel Alcubierre. He proposed something known as the Alcubierre drive, a theoretical method of faster-than-light travel that could, in theory, allow us to travel through time. The idea involves bending space-time itself. Rather than moving faster than light through space, the Alcubierre drive would stretch and contract space-time in front of a spacecraft, creating a warp bubble that moves faster than light. Inside the bubble, the spacecraft would remain stationary relative to the bubble, but the bubble itself would move faster than the speed of light. The idea of the Alcubierre drive, while purely theoretical and speculative, is grounded in the equations of general relativity, meaning it's a possible, though highly impractical, way of bending the fabric of space-time to our advantage. This concept opens the door to time travel in a very literal sense, as the bending of space-time could potentially create shortcuts through time and space, allowing us to travel vast distances almost instantaneously. But before we start imagining warp drives or time machines, we have to acknowledge that there are significant hurdles to making such travel a reality. For one thing, the energy required to warp space-time would be mind-boggling, far beyond anything we could currently generate. The equations also suggest that exotic matter with negative energy would be needed to stabilize the warp bubble, something that has yet to be discovered or even plausibly explained. So, while the idea is fun to think about, it remains far from feasible with our current understanding of physics. However, the concept of time dilation and the potential for time travel are not just science fiction, they point to some fundamental questions about how the universe works. If time is something that can be stretched or contracted, if it can be influenced by gravity and motion, what does this tell us about the true nature of time itself? This brings us to a fascinating idea proposed by a physicist named Carlo Rovelli. Rovelli, a leading figure in the field of quantum gravity, suggests that time may not be a fundamental aspect of the universe after all. Instead, he argues that time might be an emergent property, something that arises from deeper, more fundamental processes. According to Rovelli, time is not a constant backdrop against which events unfold. Rather, it's a consequence of the interactions between particles and the structure of space-time itself. In this view, time is not a universal ticking clock that flows at the same rate everywhere. Instead, it's something that emerges from the behavior of the universe at the quantum level, shaped by the way particles interact with one another. This is a radical shift from the classical view of time, and it suggests that our everyday experience of time might be an illusion, or at least a simplified version of something far more complex and elusive. So, if time is not fundamental, what does that mean for our ability to travel through it? Can we manipulate it like we manipulate space? The concept of time as an emergent property opens up new possibilities, but it also introduces a whole new set of questions. If time itself is a product of deeper laws we don't yet understand, then maybe our current understanding of time travel is too limited. We might need a new theory, one that brings together general relativity and quantum mechanics, to truly understand how time works on the most fundamental level. As we continue to explore the nature of time, one thing is clear: our understanding of space-time, gravity, and time itself is far from complete. Time dilation, while proven and observable, is just one piece of the puzzle. The deeper we go into the mysteries of space-time, the more we realize that time, like space, may be much stranger and more flexible than we ever imagined. And as we seek to understand the full implications of relativity, we're bound to uncover new insights that challenge our perceptions and take us further down the road of exploring the true nature of the universe. What's next in this journey? Well, as we've seen, time is deeply connected to gravity. The more we understand about how time flows differently depending on the curvature of space-time, the more we can begin to appreciate just how interconnected everything is in the universe. And that, my friends, is just the beginning. For centuries, gravity was understood as a force. Isaac Newton, in the late 1700s, gave us a framework for understanding this force through his law of universal gravitation. According to Newton, every object in the universe exerts an attractive force on every other object, and the strength of this force depends on two things: the masses of the objects and the distance between them. The larger the mass of an object, the stronger its gravitational pull, and the farther apart two objects are, the weaker the force between them. Gravity, in Newton's view, was an invisible force that acted instantaneously across space, pulling objects toward each other. Newton's law worked incredibly well for explaining the motions of planets, the orbits of moons and the falling of apples from trees. But as time went on, some scientists began to realize that there was more to gravity than what Newton's law could explain. One of the biggest clues came from the way light behaved. Newton's theory didn't account for how light, a form of energy, was also affected by gravity. It was as if gravity had a hidden connection to space itself, something more fundamental than a mere force between objects. Then, in the early 20th century, Einstein turned this understanding upside down with his theory of general relativity. Instead of seeing gravity as a force acting at a distance, Einstein proposed that gravity was not a force at all. Rather, it was a consequence of the curvature of space-time, the four-dimensional fabric of the universe that combines space and time into a single entity. According to general relativity, massive objects like planets and stars warp the fabric of space-time around them, and the curvature of space-time tells objects how to move. This was a monumental shift in thinking. Gravity wasn't something that acted at a distance. It was a feature of the very structure of the universe. To visualize this, think of space-time as a stretched-out sheet. If you place a heavy ball on the sheet, the ball causes a depression, or a curve, in the fabric. Smaller objects like marbles will then roll toward the heavier ball, not because the ball is pulling them directly, but because the sheet itself is curved. This analogy gives us a way to picture how planets move through curved space-time. Earth orbits the Sun not because the Sun is pulling on it, but because the curvature of space-time caused by the Sun bends the path of Earth's motion. Einstein's theory of general relativity was confirmed through several key experiments. One of the earliest and most famous was in 1920, when British astronomer Arthur Eddington observed a solar eclipse. He measured the bending of starlight as it passed near the Sun, confirming that light was indeed affected by gravity, just as Einstein's equations predicted. Over the years, as technology advanced, scientists confirmed more of Einstein's predictions, including the bending of light around other massive objects and the detection of gravitational waves, ripples in space-time caused by violent cosmic events like the collision of black holes. While Einstein's theory revolutionized our understanding of gravity, it left some open questions, particularly when it came to understanding the very small scales of the quantum world. And this is where a new and exciting approach comes in: Erik Verlinde's theory of emergent gravity. Verlinde, a Dutch theoretical physicist, suggests that gravity might not be a fundamental force at all, as Einstein and Newton thought. Instead, he proposes that gravity could emerge from the thermodynamic properties of space-time itself. Essentially, gravity might be a consequence of the way microscopic particles, like atoms and molecules, interact with each other. Verlinde's idea is rooted in the laws of thermodynamics, the science of heat and energy. He suggests that gravity arises from the entropy, or disorder of space-time. The more entropy there is in a given region of space, the more gravity we observe. This theory challenges the traditional view of gravity and offers a potential link between gravity and quantum mechanics, which would be a huge step forward in our quest for a unified theory of everything. While Verlinde's theory is still being developed and debated, it raises important questions about whether gravity is truly fundamental or whether it emerges from more basic principles. As we explore the nature of gravity, we also encounter fascinating phenomena that arise from the curvature of space-time. One of these is gravitational lensing, which occurs when light from distant objects is bent by the gravitational field of a massive object, like a galaxy or a black hole, that lies in between the light source and the observer. Gravitational lensing allows us to see objects that would otherwise be obscured, and it has provided us with some of the most stunning images in modern astronomy. For instance, when light from a distant star or galaxy passes near a massive galaxy cluster, the light bends around the cluster and creates a distorted, magnified image of the distant object. This phenomenon has been used to map the distribution of dark matter in the universe, as dark matter, which doesn't emit light, still exerts gravitational influence on the light we see. Gravitational lensing is not just a curiosity, it's a tool that scientists use to study the universe. It allows us to peer into the depths of space and observe objects that would otherwise be hidden from view. It's also a beautiful confirmation of Einstein's theory of general relativity, as it shows that light is affected by gravity, just as Einstein predicted. What's remarkable is that we can observe this bending of light not just around massive objects like stars or galaxies, but around the most mysterious and extreme objects in the universe, black holes, which brings us to gravitational waves. These ripples in space-time were first predicted by Einstein over 100 years ago, but it wasn't until 2015 that we were able to directly detect them. The LIGO collaboration, an international group of scientists, successfully measured the faint vibrations caused by the collision of two black holes. This was a groundbreaking discovery, as it confirmed Einstein's predictions and opened a new window into the universe. Gravitational waves carry information about the most violent and energetic events in the cosmos, like the merging of black holes or the explosion of supernovae. The detection of gravitational waves also gives us a glimpse into the extreme warps of spacetime that occur near black holes. These objects are the ultimate manifestation of spacetime curvature. They are regions where spacetime is so warped that nothing, not even light, can escape. Black holes form when massive stars collapse under their own gravity, creating a singularity, a point of infinite density at the center of the black hole. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. The extreme curvature of space-time inside a black hole is beyond our current understanding, and it remains one of the most mysterious aspects of the universe. Black holes challenge our understanding of physics in ways that we're still trying to comprehend. General relativity predicts their existence, but it doesn't tell us what happens at the singularity, where the curvature of space-time becomes infinite. Quantum mechanics, the theory that governs the behavior of particles on the smallest scales, also fails to describe what happens inside a black hole. This is one of the biggest unsolved problems in modern physics. How do we reconcile general relativity, which describes the large-scale structure of the universe, with quantum mechanics, which describes the tiny world of particles? As we continue to probe the nature of gravity, space-time, and black holes, we come closer to answering these fundamental questions. The more we understand about how mass and energy curve spacetime, the more we realize that gravity is not a simple force between objects. It's a deep, intrinsic feature of the universe itself, one that shapes the very fabric of space and time. And as we continue to explore the extreme environments around black holes, gravitational waves, and other cosmic phenomena, we get a glimpse of the true nature of the universe, a nature that is far stranger and more wondrous than we ever imagined. So, as we venture further into the mysteries of spacetime, we begin to see that gravity is not just a force, it is a manifestation of the fundamental structure of the cosmos, one that links space, time, and the very fabric of reality itself. And the deeper we go, the more we discover that the universe is even more fascinating, mysterious, and interconnected than we ever thought possible. When we talk about the most extreme objects in the universe, black holes always seem to take center stage. They are the ultimate manifestation of spacetime curvature, regions where gravity is so strong that nothing, no matter, no light, can escape. The very fabric of spacetime itself becomes stretched and distorted to such an extent that the laws of physics as we know them break down. Imagine an object so dense, so compact, that it warps the universe around it, creating a point of infinite density at its center, known as a singularity. This is the essence of a black hole. To understand just how strange black holes are, we first need to revisit the work of the great physicist Roger Penrose. In the 1960s, Penrose developed his groundbreaking theory of singularities. He showed that when a massive star collapses under its own gravity, the density at the center becomes infinite, forming what we call a singularity. A singularity isn't just a point. It's a place where the curvature of spacetime becomes so extreme that our current understanding of physics, including both general relativity and quantum mechanics, falls apart. At a singularity, the usual rules no longer apply, and we can no longer predict the behavior of matter and energy. This radical idea challenged the very foundations of physics. How could something so extreme exist? How could the universe allow for such a paradoxical object? Penrose's work on black holes and singularities showed that they were not just theoretical curiosities, but a natural consequence of Einstein's equations of general relativity. But even though we now accept that black holes are real, they still present some of the deepest questions about the nature of reality itself. One of the biggest mysteries surrounding black holes is what happens to information that falls into them. This question is known as the information paradox, and it was first posed by the renowned physicist Stephen Hawking in 1976. According to Hawking's theory, once something crosses the event horizon of a black hole, the boundary beyond which nothing can escape, it's lost to the universe forever. Hawking suggested that the information about the matter that falls into the black hole is erased, a concept that seemed to violate the fundamental principle of quantum mechanics, which states that information is never truly lost. This idea was deeply troubling because, in quantum mechanics, information is always preserved, even if it's transformed in some way. If black holes destroyed information, it would mean that the laws of quantum mechanics were not universal after all, and that something as fundamental as the conservation of information could be violated. The information paradox became one of the most significant unsolved problems in modern physics, one that continues to puzzle scientists today. But not all physicists agreed with Hawking's conclusion. Another prominent scientist, Don Page, proposed a different view of black holes and the information paradox. Page suggested that, rather than being lost forever, the information that falls into a black hole might be preserved in some way. He argued that the information could be encoded on the surface of the black hole, at the event horizon, a concept that would later play a key role in the development of the holographic principle. The holographic principle, which was developed by physicists Gerard 't Hooft and Leonard Susskind in the 1990s, suggests that the entire universe might be viewed as a kind of hologram. According to this idea, all the information about a three-dimensional region of space can be encoded on a two-dimensional surface that surrounds it. This might seem strange, but it's a natural extension of the idea that the information in a black hole could be stored on its event horizon. The holographic principle proposes that the entire universe, including everything inside black holes, could be encoded on a two-dimensional surface, much like a hologram stores three-dimensional information on a flat surface. This idea has profound implications for our understanding of space-time, gravity, and information. If the holographic principle is true, then black holes might not be as mysterious as we once thought. Rather than erasing information, they could be storing it in a way that we don't yet fully understand. This would resolve the information paradox and potentially offer a way to reconcile general relativity with quantum mechanics, two theories that, on their own, are incompatible in certain situations. While the holographic principle is still a theory and far from being proven, it has inspired a whole new field of research in theoretical physics, especially in the study of quantum gravity. Quantum gravity is the attempt to understand how gravity works at the quantum level, where the effects of both general relativity and quantum mechanics must be considered simultaneously. Right now, we don't have a complete theory of quantum gravity, but the study of black holes, singularities, and the holographic principle is leading the way toward a unified understanding of the universe. Another way that black holes continue to shape our understanding of the cosmos is through the study of gravitational waves. These ripples in space-time were first predicted by Einstein in 1915, but it wasn't until 2015 that scientists with the LIGO collaboration finally detected them. Gravitational waves are produced when massive objects like black holes or neutron stars accelerate or collide. These waves carry information about the event that produced them, and their detection has provided a new way to observe the universe. By studying gravitational waves, we can learn more about black holes and the extreme conditions that exist around them. For instance, when two black holes merge, they produce gravitational waves that carry information about their masses, spins, and the way they interacted before the merger. The detection of these waves allows scientists to study black holes in ways that were previously impossible. It also provides us with new insights into the nature of space-time itself and how it behaves in the presence of extremely massive objects. The study of black holes is one of the most exciting frontiers in modern physics. They represent the extremes of space-time, where the curvature of the universe becomes so intense that our current understanding breaks down. But as we continue to probe these cosmic giants, we're uncovering new mysteries and insights that could one day revolutionize our understanding of the universe. And yet, despite all that we've learned about black holes, they remain one of the greatest unsolved mysteries in physics. The singularity at the center of a black hole still defies explanation. The information paradox still looms large. The holographic principle offers a tantalizing clue, but it's far from being settled. And as we detect more gravitational waves and observe more black hole mergers, we're only beginning to understand how these objects shape the universe on the grandest scales. One thing is certain, black holes are not just strange objects floating in space. They are the key to unlocking some of the deepest secrets of the universe. They challenge everything we know about space, time, and gravity. And as we continue to study them, we move one step closer to understanding the true nature of reality itself. As we explore further into the heart of these cosmic enigmas, we'll gain new insights into the very fabric of space-time and the mysterious forces that govern the universe. In the vastness of space, events of unimaginable scale unfold, each one leaving behind ripples that travel across the fabric of space-time itself. These ripples are known as gravitational waves, and for decades they were purely theoretical, predicted by Albert Einstein over 100 years ago but never observed until the year 2015. That year, the world witnessed one of the greatest scientific breakthroughs in modern history, the detection of gravitational waves, confirming Einstein's predictions and opening a new chapter in our understanding of the universe. Gravitational waves are disturbances in space-time caused by the acceleration of massive objects, like the collision or merger of black holes. Imagine throwing a stone into a calm pond. The water ripples outward from the point of impact. Gravitational waves are a similar phenomenon, but instead of rippling through water, they ripple through the very fabric of space-time, carrying information about the cataclysmic events that created them. These waves move at the speed of light, and when detected, they provide us with a completely new way of observing the universe. The breakthrough came in September of 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. LIGO uses two extremely sensitive detectors, one in Louisiana and the other in Washington state, to measure the tiny distortions in space-time caused by passing gravitational waves. These distortions are incredibly small, on the order of 1 part in a trillion, so LIGO had to be built with extraordinary precision. The detectors work by using lasers to measure the distance between two mirrors placed far apart. When a gravitational wave passes through, it slightly stretches and compresses the distance between the mirrors, causing a tiny shift in the laser's beam. By detecting these shifts, scientists can measure the gravitational waves that caused them. The success of LIGO was due in large part to the efforts of a brilliant physicist named Rainer Weiss. Weiss, along with his colleagues, developed the concept of interferometry for detecting gravitational waves, a technique that would become the cornerstone of LIGO's success. It was Weiss who first proposed the idea of using lasers and mirrors to measure the incredibly small changes caused by gravitational waves, and his work laid the foundation for the construction of LIGO. In 2017, Weiss was awarded the Nobel Prize in Physics for his groundbreaking contributions to the discovery of gravitational waves, along with Barry C. Barish and Kip S. Thorne, who were also instrumental in LIGO's development. The detection of gravitational waves was not only a triumph for physics, but it also marked the beginning of a new era in astronomy. For centuries, astronomers have observed the universe through light, whether visible, ultraviolet, or infrared. But gravitational waves offer an entirely new way to observe the cosmos, one that doesn't rely on light at all. In fact, gravitational waves can pass through dust and gas that would normally obscure our view of the universe, allowing us to observe the most violent and energetic events in the cosmos, like black hole mergers, supernova, and neutron star collisions. Kip Thorne, one of the leading scientists behind LIGO, had long argued that gravitational waves could be detected, and that they would provide a wealth of new information about the universe. Thorne's contributions to the field of gravitational wave astronomy go beyond just the technical aspects of detection. He also developed key theoretical insights into the physics of black holes and gravitational waves, which helped guide the design of LIGO's detectors. Alongside Thorne, Alessandra Buonanno, a physicist at the Max Planck Institute, played a key role in developing the theoretical models that predict how gravitational waves would behave when produced by the merger of black holes or neutron stars. These models were crucial in helping scientists interpret the data LIGO collected and pinpoint the exact source of the waves. The first gravitational wave detection came from the collision of two black holes, each with a mass several times greater than that of our Sun. When these black holes spiraled toward each other and merged, they released an enormous amount of energy in the form of gravitational waves. This event, which took place approximately 1.3 billion light-years away, was the first direct observation of a black hole merger, and it confirmed many of the predictions made by general relativity. The waves generated by the collision travelled across the universe, eventually reaching Earth and being detected by LIGO. Since that first detection, LIGO has observed many more gravitational wave events, including mergers of neutron stars, which are the remnants of massive stars that have exploded in supernovae. One of the most significant discoveries from LIGO was the detection of a neutron star merger in August of 2017. This event was particularly remarkable because it was accompanied by the emission of electromagnetic radiation, including gamma rays and visible light, which allowed scientists to study the merger in multiple ways. This discovery confirmed that neutron star mergers are a key source of heavy elements in the universe, such as gold and platinum, and it opened up a new field of multi-messenger astronomy, where scientists combine data from gravitational waves, light, and other forms of radiation to better understand cosmic events. The discovery of gravitational waves has far-reaching implications for our understanding of the universe. For one, it allows us to observe objects like black holes that are completely invisible to traditional telescopes. Black holes, which don't emit light, have long been a source of mystery. But by studying the gravitational waves they produce, we can learn more about their mass, spin, and even the way they interact with their surroundings. The detection of gravitational waves also provides a new way to test the predictions of general relativity in extreme conditions. By studying the ripples in spacetime caused by black hole mergers, we can gain deeper insights into the nature of gravity and spacetime itself. But gravitational waves also offer a glimpse into some of the most violent and energetic events in the universe. The merging of two black holes, for example, releases as much energy as the Sun will emit over its entire lifetime. Yet this energy is spread out over the entire universe in the form of gravitational waves. These waves are incredibly weak by the time they reach Earth, but the precision of LIGO's detectors allows us to measure even the tiniest distortions in space-time. As we continue to detect more gravitational waves, we are learning more about the structure of the universe on both large and small scales. From the dynamics of black hole mergers to the evolution of galaxies, gravitational waves provide a new window into the universe that we never had before. And as the field of gravitational wave astronomy continues to evolve, we will only deepen our understanding of the cosmos and the forces that shape it. Gravitational waves also hold promise for a deeper understanding of the large-scale structure of the universe. The ripples they create carry information about the objects and events that cause them, but they also carry a signature of the space through which they travel. By studying these waves, we can learn about the distribution of mass and energy in the universe, including the role of dark matter and dark energy in shaping the cosmos. This could ultimately help us answer some of the most profound questions about the universe's origin, evolution, and ultimate fate. As we look ahead, the discovery of gravitational waves represents just the beginning of what promises to be an exciting new era in our understanding of the universe. The ability to hear the cosmos, to observe the most extreme events in the universe in real time, is nothing short of revolutionary. And as the technology behind gravitational wave detection continues to improve, we can expect even more remarkable discoveries in the years to come. Through these ripples in space-time, we're learning to listen to the very heartbeat of the universe itself. General relativity isn't just a theory that explains the behavior of objects in motion or the bending of light. It's a framework that fundamentally shapes our understanding of the entire universe, from the way galaxies are formed to the expansion of the cosmos itself. At its core, general relativity tells us that the universe is not a static, unchanging backdrop. Instead, it's a dynamic living system, where the very fabric of space and time is shaped by the mass and energy contained within it. One of the most profound implications of Einstein's theory is that gravity, far from being a force acting at a distance, is the result of the curvature of space-time itself. The more massive an object, the more it warps the fabric of space-time, and this curvature dictates how other objects move through the universe. It's this very idea that allows general relativity to give us a detailed understanding of the large-scale structure of the universe, from the motion of stars and galaxies to the overall expansion of the cosmos. In the early 20th century, as Einstein's theories were being validated, scientists started to notice something strange. Galaxies appeared to be moving away from each other, as though the universe was expanding. This discovery was made by Edwin Hubble in the 1920s, when he observed that the light from distant galaxies was shifted toward the red end of the spectrum, indicating that they were receding from us. This was a direct consequence of the expansion of space itself, as predicted by Einstein's equations. But there was more to the story. As scientists began to study the rate of expansion, they found that the universe wasn't just expanding at a constant rate, it was accelerating. This led to the discovery of two mysterious phenomena, dark matter and dark energy, that play key roles in the universe's large-scale structure. Dark matter, which accounts for roughly 25% of the universe's total energy content, is a form of matter that doesn't emit, absorb, or reflect light, making it invisible to telescopes. But despite its elusiveness, dark matter's presence is felt through its gravitational influence. It's responsible for the way galaxies spin, and without it, the galaxies would fly apart because there wouldn't be enough gravitational pull to hold them together. One of the key pieces of evidence for dark matter came from the work of Vera Rubin, a pioneering astronomer who, in the 1970s, observed the rotation curves of galaxies. She discovered that the stars at the outer edges of galaxies were moving much faster than expected based on the visible matter in the galaxy. This indicated that there was some unseen mass, dark matter, providing the extra gravitational pull needed to keep the stars in orbit. Dark energy, on the other hand, is a more recent discovery. In the late 20th century, astronomers found that the expansion of the universe wasn't just slowing down due to gravity, as they had once thought, but was actually accelerating. This led to the hypothesis of dark energy, a mysterious force that makes up about 70% of the universe's energy content, and is responsible for driving the accelerated expansion. While we don't yet fully understand what dark energy is, it appears to be the dominant force shaping the evolution of the universe. Some theorists suggest that dark energy might be related to the cosmological constant that Einstein originally introduced into his equations only to later abandon. In this view, dark energy is a property of space itself, causing the fabric of space-time to stretch and pull galaxies apart. The discovery of dark matter and dark energy has reshaped our understanding of the universe's structure and its fate. These mysterious substances are key players in the story of the cosmos, and without them, the universe as we know it wouldn't exist. However, the presence of dark matter and dark energy also suggests that there is much more to the universe than meets the eye. Much of the universe's energy content is hidden from our direct view, and the true nature of these phenomena remains one of the most significant puzzles in modern science. While general relativity has provided us with a powerful framework for understanding the large-scale structure of the universe, it doesn't tell us the whole story. In fact, it raises some important questions about the nature of the universe itself. For example, if the universe is expanding, what is it expanding into? And if space itself is stretching, where did it come from? These are questions that led to the development of alternative cosmological theories, such as the idea of a multiverse and the concept of cosmic inflation. J. Richard Gott, a theoretical physicist, is known for his work on the shape and structure of the universe. In the 1980s, he proposed that the universe might have a finite but unbounded shape, similar to the surface of a sphere. This idea suggested that the universe could be infinite in size, but still have no edge or boundary. Gott's work helped to challenge our understanding of the universe's shape and led to more questions about how it began and how it will end. Another influential figure in cosmology is Alan Guth, who is best known for his development of the inflationary model of the universe in the 1970s. According to Guth's theory, the universe underwent a rapid, exponential expansion in the first fraction of a second after the Big Bang. This period of inflation helped to explain why the universe is so uniform on large scales, as it would have smoothed out any initial irregularities. Inflation also provides a way to understand the origin of the universe, as it suggests that space itself is constantly being created and stretched, providing a kind of seed for the formation of matter and galaxies. Both Gott's and Guth's work has helped to shape our modern understanding of the universe, providing us with a framework for understanding its vastness and its beginnings. But while these theories have been influential, they are still incomplete, and many questions remain about the true nature of the cosmos. General relativity, with its focus on the curvature of space-time, has been instrumental in our understanding of the large-scale structure of the universe. It has given us insights into the formation and motion of galaxies, the role of dark matter and dark energy, and the overall expansion of the universe. Yet, as we've seen, the universe's structure is not fully explained by general relativity alone. Theories like inflation and the multiverse challenge our notions of space and time, and they push the boundaries of what we understand about the cosmos. As we continue to explore the universe's structure, we must also consider its future. The discovery of dark energy and the acceleration of the universe's expansion raises the possibility that the universe may continue to expand forever. But what will that future look like? Will galaxies drift farther apart until the universe becomes cold and dark? Or will some other force or phenomenon intervene to alter the course of cosmic evolution? These questions point toward a deeper understanding of the universe's fate, one that will require not only general relativity, but also new theories that can bring together the forces of gravity, quantum mechanics, and dark energy. As we look forward, the mysteries of the universe's origin, its expansion, and its ultimate fate remain some of the most exciting and profound questions in science. And the more we learn, the closer we come to unraveling the deep interconnected story of the cosmos itself. When we look up at the stars, it's easy to get lost in the beauty of the night sky, marveling at the vastness of the universe and the endless possibilities it holds. But as we peer into the cosmos, we also begin to wonder, what will happen to all of this? What will be the ultimate fate of the universe and how will it end? Will it continue to expand forever, or will it eventually collapse in on itself? These are the kinds of questions that cosmologists have been grappling with for decades, and the answers are far from simple. There are several theories about the universe's end, each offering a different scenario for what might happen to the vast cosmic expanse that we observe today. These theories are based on our current understanding of the laws of physics, but new discoveries, particularly regarding dark energy and the expansion of the universe, continue to shape our predictions for the future. Let's explore a few of the most widely discussed possibilities. One of the most well-known scenarios for the universe's future is the Big Freeze. According to this model, the universe will continue expanding indefinitely, with galaxies moving farther and farther apart over time. As space itself stretches, stars will burn out, and the universe will become increasingly cold and dark. Eventually, stars will no longer form, and the universe will reach a state of thermodynamic equilibrium, where no energy flows and no processes can occur. In this scenario, the universe will slowly decay into a state of heat death, where everything is frozen in place, and time as we know it comes to a standstill. The Big Freeze seems to be the most likely outcome based on our current understanding of the universe, particularly in light of the discovery that the expansion of the universe is accelerating due to the influence of dark energy. Dark energy is a mysterious force that makes up about 70% of the universe's energy content. It's responsible for the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. The exact nature of dark energy remains one of the biggest puzzles in cosmology. Some scientists speculate that it might be linked to the cosmological constant, a term Einstein originally introduced into his equations of general relativity in 1919 to allow for a static universe. Though Einstein later abandoned this idea, the concept of a constant energy density throughout space has made a comeback as an explanation for dark energy. The discovery that the expansion of the universe is speeding up rather than slowing down suggests that dark energy is a dominant force in the universe's future. As the universe expands faster and faster, the Big Freeze scenario becomes more likely, with galaxies, stars, and eventually all matter drifting apart as the universe reaches its final cold, dark state. However, not all theories of the universe's end point to a cold, dark future. There's another possibility, the Big Rip. In this scenario, the expansion of the universe accelerates so dramatically that eventually the very fabric of space-time itself begins to tear apart. As dark energy continues to push galaxies farther apart, the gravitational pull that holds stars, planets, and even atoms together would eventually become too weak to keep them intact. Galaxies would break apart, stars would be torn from their orbits, and even the atomic structure of matter would be shattered. The Big Rip would represent the ultimate destruction of the universe, where everything is torn asunder in a final cataclysmic event. This scenario is still speculative, and scientists are working to understand whether the accelerating expansion of the universe will continue indefinitely, or whether it will eventually slow down or reverse. Then there's the Big Crunch, a theory that proposes the opposite of the Big Freeze. In this model, the expansion of the universe eventually slows down and reverses, causing the universe to collapse in on itself. As galaxies, stars, and all matter are pulled back together by gravity, the universe would shrink and the temperature would rise, leading to a dramatic and catastrophic event where everything contracts into a singularity. The Big Crunch is a possible outcome if the density of the universe is high enough for gravity to eventually overcome the effects of dark energy and the expansion slows. While the Big Crunch was once considered a likely scenario, the discovery of dark energy has made it seem less probable, as dark energy appears to be pushing the universe apart rather than pulling it together. But there's another layer of complexity to these theories, one that stretches the boundaries of our imagination and forces us to think about the universe on an entirely different scale. The multiverse theory, which suggests that our universe might be just one of many universes, each with its own set of physical laws, has gained traction among some cosmologists. The idea that there could be multiple, perhaps infinite universes, each with different properties, has profound implications for our understanding of the universe's fate. The concept of the multiverse comes from several different sources, including the work of physicists like Hugh Everett and his many worlds interpretation of quantum mechanics. Everett proposed that every time a quantum event occurs, such as the observation of a particle, it creates a branching point, where each possible outcome of that event happens in a separate parallel universe. According to this view, the universe is constantly splitting into multiple realities, with each one representing a different outcome of quantum events. This idea has been expanded in the context of cosmology through the theory of cosmic inflation, which was developed by Alan Guth in the 1970s. Guth's inflationary model suggests that in the very early moments of the universe, space itself expanded exponentially in a fraction of a second, smoothing out any irregularities. But this process of inflation might not have ended in our universe alone. Some versions of the inflationary theory suggest that inflation is a never-ending process, creating bubbles of space-time that each form their own universe. In this view, our universe is just one of countless others, each with its own laws of physics and initial conditions. The multiverse theory offers a new perspective on the fate of the universe. Rather than a single, inevitable end, it suggests that the universe might be part of a larger, ever-expanding collection of universes, each with its own potential fate. The multiverse theory introduces a level of speculation that challenges our conventional understanding of the universe, but it also opens the door to new ways of thinking about the cosmos and its future. If our universe is just one bubble in a multiverse, then the ultimate fate of our universe might not matter in the grander scheme of things. After all, there may be countless other universes with their own histories and endings. While the multiverse is still a speculative idea, it challenges us to think beyond the confines of our own universe and consider the possibility that the cosmos is far more vast and complex than we've ever imagined. And as we continue to explore the origins and evolution of the universe, we may one day gain insights into how our universe fits into this larger multiversal picture. As we look to the future of the universe, the role of dark energy and the expansion of space continue to shape our predictions. Whether the universe experiences a big freeze, a big rip, or something entirely different, the fate of the cosmos is intricately tied to the forces that drive its expansion. But the deeper questions about the multiverse, parallel universes, and the true nature of space and time remain on the horizon, waiting for new theories and discoveries to illuminate the path forward. As we continue to explore these mysteries, we may one day unlock the ultimate fate of the universe itself, and in doing so uncover truths about the nature of existence that we can hardly begin to comprehend. At the heart of modern physics lies one of the most fascinating and perplexing puzzles. How do we reconcile the two most successful theories of the universe, general relativity and quantum mechanics? Each theory has been tested and confirmed in its own domain. General relativity, developed by Albert Einstein, beautifully explains the behavior of massive objects, like planets, stars, and black holes, and it shapes our understanding of the large-scale structure of the universe. Quantum mechanics, on the other hand, governs the behavior of the tiniest particles in the universe, from electrons to photons, and is the foundation of modern chemistry and technology. Yet, when it comes to combining these two frameworks, things get complicated. The issue arises because general relativity describes a smooth, continuous fabric of space-time that is curved by the presence of mass and energy. In contrast, quantum mechanics describes a world where particles are discrete and probabilistic, existing in a state of superposition until measured. These two views, one smooth and continuous, the other discrete and uncertain, seem to contradict each other, and finding a way to unify them has become one of the greatest challenges in theoretical physics. One scientist who has contributed to this search for a unifying theory is Lee Smolin, a physicist known for his work on quantum gravity. Smolin proposed the idea of quantum foam, a concept that challenges our traditional understanding of space-time. In his view, at the smallest scales, smaller than even atoms, Space-time is not smooth, but rather a frothy, chaotic structure made up of tiny, fluctuating bubbles of space-time. These fluctuations arise from the uncertainty principle in quantum mechanics, which tells us that we cannot precisely measure both the position and momentum of particles at the same time. Smolin's theory suggests that the fabric of space-time itself behaves like a quantum system, constantly fluctuating and evolving in unpredictable ways. This quantum foam could potentially offer a new understanding of the fundamental nature of space-time and provide a path toward reconciling general relativity and quantum mechanics. But Smolin's ideas are not the only ones being explored in the quest for a theory of quantum gravity. Another influential approach comes from Hugh Everett, who proposed the many-worlds interpretation of quantum mechanics in 1957. Everett's theory radically changes how we think about quantum states and the nature of reality. According to Everett, when a quantum measurement is made, all possible outcomes of that measurement don't collapse into one reality. Instead, each possible outcome happens in a different parallel universe. This means that the universe splits into multiple coexisting realities, each representing a different possible outcome of every quantum event. The implications of Everett's many-worlds interpretation are profound. It suggests that our reality is just one of an infinite number of parallel realities, all existing simultaneously. In the context of quantum mechanics, this view provides a way to avoid the problem of wave function collapse, where a quantum system seems to choose a specific state upon observation. Instead, in Everett's view, all possibilities are realized, and our perception of one outcome is merely the result of the universe we happen to inhabit. While the many-worlds interpretation remains controversial, it has gained traction among some physicists as a possible explanation for the strange behavior of quantum particles. Everett's ideas have important implications for how we think about time as well. In the many-worlds framework, time is not a single, linear progression that flows in one direction. Instead, every quantum event creates a branching of the timeline, leading to multiple parallel timelines that evolve independently. This challenges our traditional understanding of time as a fixed and linear flow. Instead, time in Everett's view could be seen as a vast network of timelines, each branching out and evolving according to its own set of quantum outcomes. While Smolin and Everett's ideas offer intriguing possibilities, there are other theories that attempt to bridge the gap between general relativity and quantum mechanics. One of the most well-known is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the various particles we observe in nature. String theory offers a potential framework for unifying the forces of nature: gravity, electromagnetism, the strong nuclear force and the weak nuclear force, into a single coherent theory. However, string theory is still in its early stages, and many questions remain about its validity and its ability to fully explain quantum gravity. Another approach to quantum gravity is loop quantum gravity, which was developed as an alternative to string theory. This theory suggests that space-time itself is quantized, meaning that at the smallest scales, space and time are made up of discrete chunks rather than being continuous. In this view, the fabric of space-time is like a network of tiny loops, and gravity arises from the interaction of these loops. Loop quantum gravity has the potential to provide a quantum description of gravity, and it could offer new insights into the nature of black holes and the very beginning of the universe, where both quantum mechanics and general relativity must be taken into account. While both string theory and loop quantum gravity hold promise, neither has yet provided a complete experimentally verified theory of quantum gravity. The search for a unified theory that can combine general relativity and quantum mechanics remains one of the most exciting and elusive goals in physics. These theories are still being developed and tested, and they could one day provide the framework for understanding the most fundamental aspects of the universe. As we explore these different theories and ideas, it's important to remember that they are all attempting to answer the same basic question: how does the universe work at the most fundamental level? And at the heart of this question is the issue of time. Time is one of the most mysterious aspects of the universe, and it plays a central role in both general relativity and quantum mechanics. In general relativity, time is intricately linked to the geometry of space-time, and its passage can be stretched or compressed depending on gravity and motion. In quantum mechanics, time is treated as a background parameter, something that ticks away in the background while particles interact in probabilistic ways. But as we attempt to reconcile these two theories, time itself becomes a key challenge. For instance, in general relativity, time is not the same everywhere. It is affected by gravity, and time can move faster or slower depending on the curvature of space-time. This means that time is flexible and relative, not absolute. In contrast, quantum mechanics treats time as a constant, a steady parameter that flows uniformly across all systems. This difference in how time is treated in the two theories has been one of the major obstacles in attempting to unite them into a single framework. As we continue to explore the quantum realm and the strange behavior of particles, we must also grapple with the nature of time itself. Is time a fundamental property of the universe, or is it something that emerges from deeper, more fundamental principles? Is it a constant, unchanging force that flows in one direction, or is it something more fluid, shaped by the very structure of space-time? The answers to these questions may hold the key to understanding the true nature of the universe. As we search for a unified theory of quantum gravity, time will continue to be a central theme, and in the quantum world, where the rules of reality seem to bend and twist in ways that defy our intuition, time itself might be far stranger than we can imagine. When we talk about time, it's easy to think of it as something simple and straightforward, something that ticks away consistently, moment after moment. We live by time, clocks, calendars, deadlines. But in the quantum world, time behaves in ways that completely defy our classical understanding. In fact, time in quantum mechanics isn't the fixed, flowing river we imagine it to be. Instead, it's a far more mysterious, paradoxical concept that challenges the very idea of what time really is. At the heart of the quantum world lies the concept of quantum entanglement, a phenomenon that seems to break all the rules we associate with time. In quantum entanglement, two particles can become so deeply linked that the state of one particle instantly affects the state of the other, no matter how far apart they are. This connection happens faster than the speed of light, which seems impossible according to classical physics. But more importantly, it suggests that the concept of time might not behave in the way we think. Normally, we think of events happening in a linear sequence. A happens, then B happens, then C follows. But in the quantum world, entangled particles appear to communicate instantaneously, even if they are light years apart. This raises the question, if information can travel faster than the speed of light, what does that mean for time itself? Does time flow in the same way for everything? Does the order of events always matter, or is time itself as strange and fluid as the particles it governs? One physicist who has offered a new perspective on the nature of time in the quantum world is Carlo Rovelli. Rovelli suggests that time, rather than being a fundamental feature of the universe, might be an emergent property. In his view, time doesn't exist in the way we commonly think of it. It's not an independent entity that ticks away regardless of the universe's state. Instead, time emerges from the relationships between the quantum events that occur in the universe. This idea challenges the traditional understanding of time as something that exists independently of the particles, fields, and forces that make up the universe. Rovelli's perspective is influenced by the work of quantum gravity and his own research in loop quantum gravity, a theory that attempts to reconcile quantum mechanics with general relativity. According to Rovelli, the very nature of time depends on the interactions of the smallest elements of space-time. Just as space itself is not a passive stage, time is not a background player either. It's a feature of how the universe behaves at the most fundamental level, arising from the quantum interactions that govern matter and energy. This idea turns the classical view of time on its head. Instead of time being an ongoing, continuous thread that everyone experiences the same way, Rovelli suggests that time is something more like a result or outcome of quantum processes. It's not that time doesn't exist, it's just that it's not the same for everyone, and it's not as universal as we might think. This approach offers a new way of thinking about the arrow of time, the idea that time has a direction, from the past to the present and into the future. But if time is an emergent property, then how do we make sense of the way we experience time in our everyday lives? How do we explain the flow of time that seems so undeniable? To explore that, we turn to time symmetry, a fundamental principle in quantum mechanics that says the laws of physics don't change whether time moves forward or backward. In other words, the equations that govern the behavior of particles are symmetrical in time. They would work the same whether time is running forward or backward. This symmetry is a fascinating concept because it suggests that the arrow of time, our perception of time flowing in one direction, may be more of an illusion. Time symmetry works well at the level of fundamental particles, but when it comes to the larger macroscopic world we live in, the symmetry is broken. That's where the second law of thermodynamics comes into play. It tells us that in any isolated system, disorder or entropy always increases over time. So, while the fundamental laws of physics might be symmetric, the processes that we observe in the real world tend to move from order to disorder. This increase in entropy gives rise to the arrow of time that we experience. Things naturally move from a state of lower disorder to higher disorder, from the past to the future. It's this clash between time symmetry at the quantum level and the directionality of time we observe in our everyday lives that makes time such a paradoxical concept in quantum mechanics. The idea that time could be both emergent and symmetrical, while still seeming to flow in one direction, is a mind-bending idea that takes us to the very limits of what we understand about time. As we delve deeper into the quantum world, these strange paradoxes only multiply. If time itself isn't what we think it is, what does that mean for the past, present, and future? Are they real, tangible things, or are they merely perspectives on a deeper, more abstract reality? Does time flow for everyone the same way, or is it as subjective as the particles we observe? The implications of these questions are enormous, and they bring us to the very edge of physics and philosophy. Quantum mechanics has already taught us that the universe behaves in ways that defy our intuition. Particles can be in multiple states at once. They can influence each other instantaneously over great distances, and their behavior can be affected by the act of measurement. All of these strange properties challenge the classical deterministic view of the universe that we have come to rely on. But time is where things get truly mind-bending. As we consider how time functions at the quantum level, we must confront some of the biggest questions in physics. What is time, really? Is it an illusion created by the interactions of particles? Is the past fixed, or can it change based on the quantum events of the present? Can we move backward through time, or is time's direction a fundamental, unchangeable feature of the universe? The quest to answer these questions is ongoing, and it requires a radical rethinking of our assumptions about the universe. Time, it seems, is not the simple, steady thing we once thought it was. It is tied up with the deepest, most fundamental mysteries of the cosmos, and it may hold the key to understanding how the universe works at its most basic level. As we continue to explore these ideas, we'll find that the line between reality and our perception of it becomes increasingly blurry. The more we understand about the quantum world, the more we realize that the nature of time and reality itself may be far stranger than we ever imagined. And as we move forward in our search for a unified theory of everything, time will continue to be one of the greatest challenges we face, shaping not just our understanding of the universe, but our very understanding of what it means to exist. As we explore the vast depths of space-time, gravity, and time, we begin to confront some of the most fundamental and mind-bending questions about the nature of reality itself. What does it mean for something to be real? Is the universe we experience the ultimate reality, or is it an illusion shaped by the way we perceive it? How do concepts like space-time and time itself impact our understanding of what is truly out there? To begin, let's consider the concept of space-time. In the framework of general relativity, space-time isn't just a passive stage on which events happen, it's an active participant in the unfolding of the universe. Massive objects like stars and planets curve space-time, and this curvature dictates the motion of everything from light to galaxies. This view of space-time as a dynamic, flexible entity challenges the classical view that space and time are fixed and unchanging. But if space-time itself is malleable, then how do we know what's real? Is reality something that exists independently of our perception of it, or is it more like a projection shaped by the fabric of space-time? One physicist who explored these questions in depth was David Bohm, who proposed a radically different way of thinking about the universe. Bohm's ideas were in part inspired by quantum mechanics, which shows us that the universe operates in ways that defy our intuitive understanding. In his work, Bohm proposed that the universe is not a collection of independent objects as we often imagine, but rather a single, interconnected whole. He suggested that what we perceive as separate particles and events is actually part of a deeper, more fundamental reality that he called the implicate order. In Bohm's view, space and time are not fundamental aspects of reality. Rather, they emerge from this deeper order, which we cannot directly perceive. According to this perspective, the universe is not a collection of objects moving through space and time, but an indivisible whole, where everything is connected in ways we cannot yet fully comprehend. Bohm's ideas force us to rethink what we mean by real. If reality is not a collection of independent objects, but a deeper, hidden unity, then what we experience as space and time might only be surface-level aspects of a much more intricate and interconnected system. This view suggests that the universe, as we see it, is not necessarily the true reality, but rather an unfolding of a deeper, non-local order that exists beyond our ordinary perception. It raises the question, if space and time are just aspects of a deeper reality, then can we trust our perception of the world around us? Is what we see, hear, and touch really all there is to reality, or is there something more, something we can't see with our senses? One of the most intriguing aspects of quantum mechanics that touches on the nature of reality is the observer effect. In the quantum world, particles exist in a state of superposition, meaning they can be in multiple states at once, until they are observed or measured. The act of measurement seems to collapse the superposition into a single definite state. This phenomenon challenges our classical view of reality, where we assume that objects have definite properties, independent of whether we observe them or not. In the quantum realm, the very act of observation plays a fundamental role in determining what exists and what doesn't. This has profound implications for our understanding of reality. It suggests that reality may not be as fixed and objective as we once thought. Instead, it may be more fluid, more subjective, shaped by our interaction with it. The observer effect suggests that reality could be influenced by our consciousness or perception, and this brings us to one of the central philosophical questions of modern physics. Does the universe exist independently of us, or is it a product of our minds? One possible answer to this question comes from the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. According to this interpretation, all possible outcomes of a quantum event actually occur, each in its own separate parallel universe. In other words, every time a quantum event takes place, the universe splits into different branches, with each branch representing a different possible outcome. This interpretation challenges our traditional view of time and reality, as it suggests that there are multiple versions of reality, each existing simultaneously. In the many worlds framework, our experience of reality is just one of many possible timelines, and the act of observation doesn't collapse the wave function, but simply places us in one of these many possible worlds. The many worlds interpretation offers a fascinating way to think about reality. If every possible outcome of a quantum event happens in a separate universe, then the idea of a single, objective reality becomes less clear. Instead, reality becomes a multiverse of parallel worlds, each containing its own version of events. This idea takes the fluidity and uncertainty of quantum mechanics and extends it to the very structure of reality itself. In this view, what we perceive as real is just one version of a vast branching multiverse, where every possible event occurs somewhere. But even if we don't fully embrace the idea of the many worlds, the concept of the block universe offers an alternative way of thinking about time and reality. The block universe is a philosophical idea that suggests the past, present, and future all exist simultaneously in a kind of four-dimensional block of space-time. In this view, time is not something that flows in one direction, but is rather a fixed, unchanging dimension, much like space. Everything that has ever happened, is happening, and will ever happen, exists at once in this block, and we simply perceive time as flowing, because we are confined to experiencing it in a particular order. In this way, the flow of time might be nothing more than an illusion, a product of our limited perspective within the block. The block universe challenges our common understanding of time as something that flows from the past into the future. If the block universe is correct, then time is more like a landscape we move through, rather than a river we ride. The past, present, and future are all laid out before us, and we simply experience one slice of it at a time. This idea resonates with the theory of relativity, which tells us that time is not universal. It can stretch, compress, and behave differently depending on where we are and how fast we're moving. In the block universe, This flexibility of time becomes even more pronounced as the entire timeline of the universe is already set and we're just living through it. This concept also ties into our earlier exploration of quantum mechanics and the observer effect. If time is an illusion, and if reality is not as fixed as we once thought, then the question arises, what does this mean for the nature of the universe itself? Are we living in a universe that's constantly unfolding, with time flowing like a river? Or is the universe more like a frozen block, with everything already laid out, and our experience of time just a byproduct of our limited perspective? These are the kinds of deep questions that arise when we start to think about the nature of time and reality in the context of space-time and quantum mechanics. Whether time is an illusion, a subjective experience, or an emergent property of the quantum world, it challenges our fundamental understanding of the universe. The more we explore these questions, the more we realize that our perception of reality may not be as straightforward as we once believed. As we continue to search for answers, we may find that time, and the very fabric of reality itself, is far stranger and more complex than we could have ever imagined. And as we look to the future, these questions about time, space-time, and the nature of reality will continue to shape our quest for understanding the universe and our place within it. The idea that we might not be living in just one universe, but in a multiverse, has become a topic of great interest in modern cosmology and quantum mechanics. The multiverse theory suggests that our universe is just one of many, possibly infinite universes that coexist, each with its own set of physical laws and conditions. The notion of multiple universes raises profound questions about the very nature of reality and our place within it. The concept of the multiverse is not a recent development, though. It has its roots in the exploration of cosmological and quantum theories that began to shape our understanding of the universe in the 20th century. As scientists delved deeper into the nature of space, time, and the laws of physics, it became increasingly clear that our universe might not be the only one. Instead, the multiverse could be an extension of these ideas, an inevitable consequence of the fundamental workings of the cosmos. One of the prominent cosmologists who has contributed to the development of the multiverse idea is Max Tegmark, who introduced his mathematical universe hypothesis. Tegmark's hypothesis suggests that the physical universe is not just governed by mathematics, but that it is mathematics itself. In this view, the universe is a mathematical structure, and all possible mathematical structures, essentially all possible universes, exist. According to this hypothesis, every possible configuration of particles, forces, and laws of physics is realized in some universe within a vast multiverse. In this sense, every conceivable version of reality, no matter how strange or unlikely, has a place in the multiverse. This idea challenges the traditional view that our universe is the only one with the laws of physics that we observe. Instead, Tegmark's hypothesis suggests that our universe is just one of many, each potentially with different physical laws, constants, and even dimensions. For instance, in one universe, the laws of gravity might behave in a completely different way, or the fundamental forces might be arranged in an entirely unique configuration. The implications of Tegmark's hypothesis are staggering, as it implies that every possible version of reality, including alternate versions of ourselves and our universe, could exist somewhere in the vast multiverse. While the idea of a multiverse might seem outlandish, it is grounded in the frameworks of general relativity and quantum mechanics, two of the most successful theories in modern physics. Both of these theories suggest that the universe we observe may not be the only one. General relativity, as developed by Albert Einstein, describes the large-scale structure of the universe, including the behavior of massive objects like stars, galaxies, and black holes. One of the consequences of general relativity is the idea of the Big Bang and the subsequent expansion of space. As the universe began from a singularity and expanded outward, the fabric of space-time itself stretched, leading to the creation of the universe we observe today. But general relativity also suggests that other universes could have emerged in a similar way, with their own separate space and time, each expanding from its own singularity. These parallel universes would exist independently of ours, with no way of interacting with or observing each other, but still within the broader context of the multiverse. Quantum mechanics, the theory that governs the behavior of the smallest particles in the universe, offers a complementary view of the multiverse. According to the many worlds interpretation, proposed by Hugh Everett in the 1950s, every quantum event causes the universe to split into multiple branches, each corresponding to a different outcome of that event. For example, when an electron in an atom is in a superposition of states, it doesn't just choose one state when observed. Instead, the universe splits, with one branch representing the electron in one state and another branch representing the electron in a different state. In this view, the universe constantly splits, creating an ever-growing multiverse of parallel realities where every possible outcome of every quantum event occurs in a different universe. This many-worlds interpretation offers a potential explanation for the multiverse, suggesting that the branching of the universe happens at every quantum interaction, creating an infinite number of possible worlds. The universes that exist in parallel to ours may be nearly identical to ours in some respects, or they may be vastly different. In some universes, events might have unfolded differently. Perhaps in one universe, a different outcome occurred during a historical event, or perhaps the laws of physics themselves operate in a completely distinct way. While the idea of parallel universes or multiple realities may seem like science fiction, there is a strong theoretical foundation for these ideas. The framework of quantum mechanics allows for the existence of multiple realities through the many possible states of quantum systems. The possibility of a multiverse is further supported by cosmological models such as cosmic inflation, which suggests that the rapid expansion of the universe during the Big Bang could have led to the creation of other universes, each with its own distinct properties. Another aspect of the multiverse that has generated considerable interest is the idea of bubble universes, which arise from the theory of inflation. According to this theory, the early universe underwent an extremely rapid period of expansion, stretching from a subatomic scale to vast distances in the blink of an eye. This inflationary period could have created multiple bubbles of space-time, each of which evolved into a separate universe. In this model, each bubble universe could have different physical constants, laws of physics, and dimensions, leading to a diverse and varied multiverse. As fascinating as the idea of the multiverse is, it raises some deep philosophical questions. If there are multiple universes, each with its own set of physical laws, does that mean that anything that is possible can occur somewhere in the multiverse? Are all possibilities realized? Or is there a deeper structure that limits the types of universes that can exist? And if our universe is just one of many, what does that mean for the meaning and significance of our own reality? Are we just one of countless versions of ourselves in a vast cosmic landscape, or is there something uniquely important about the universe we live in? These questions touch on the very nature of reality and our place in it. If the multiverse is real, then the universe we observe might not be as special as we once thought. The vastness of the multiverse could mean that our universe is just one among countless others, each with its own history, structure, and possibilities. But this raises the question, if every possible outcome exists somewhere in the multiverse, what does that say about our choices, our fate, and the nature of free will? If everything is predetermined in some sense, does that make our actions any less meaningful? These are profound philosophical questions that extend far beyond the realm of physics. The idea of the multiverse also brings us to the question of fine-tuning. Our universe appears to be finely tuned to support life as we know it. The constants of nature, such as the strength of gravity and the electromagnetic force, seem to be just right for the formation of stars, planets, and life. In a multiverse, the concept of fine-tuning could be explained by the idea that our universe is simply one of many that happen to have the right conditions for life. In this view, we exist in a universe where the conditions just happen to be right for life, while in other universes different conditions could prevail. The multiverse theory also raises questions about the observable universe. If there are infinite universes, does it matter if we can observe them or not? Are we restricted to the universe we live in, or could there be ways to peek into other realities, even if they are fundamentally separate from our own? These questions push the limits of what we can know and understand, and they challenge our conventional ideas of space, time, and reality itself. As we continue to explore the implications of the multiverse, one thing becomes clear. The more we understand about the cosmos, the more we realize how much we don't know. The multiverse is a fascinating idea that extends our understanding of the universe far beyond the familiar boundaries of space and time. It forces us to reconsider our place in the cosmos and our understanding of what is truly real. Whether or not the multiverse exists, it serves as a reminder that the universe is far stranger and more mysterious than we can possibly imagine. And as we continue to ask the big questions about the nature of existence, the multiverse may be just one of many possibilities we will explore in the search for answers. For over a century, general relativity and quantum mechanics have been the two pillars of modern physics. General relativity, developed by Albert Einstein, explains the behavior of massive objects and the curvature of space-time, governing everything from planets orbiting stars to the bending of light around black holes. Quantum mechanics, on the other hand, deals with the strange behavior of the smallest particles in the universe, dictating how atoms, electrons, and photons interact. These two theories have revolutionized our understanding of the universe in their respective realms, but they are fundamentally incompatible when it comes to understanding the universe at its deepest level, where both gravity and quantum effects play a significant role. The search for a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, is one of the most exciting and challenging endeavors in modern physics. Scientists have long recognized that the current understanding of these two theories is incomplete, particularly in situations where both gravitational and quantum forces are at play, such as near black holes or in the very early moments of the Big Bang. To bridge the gap between the macro world of general relativity and the micro world of quantum mechanics, physicists have proposed several possible solutions. Two of the most prominent approaches are loop quantum gravity and string theory. Loop quantum gravity is an approach that attempts to describe gravity using the principles of quantum mechanics. In this theory, spacetime itself is quantized, meaning that space and time are made up of discrete, indivisible chunks, much like matter is made up of atoms. The theory suggests that at the smaller scales, spacetime is not smooth and continuous, as described by general relativity, but rather granular and discrete. This is in stark contrast to Einstein's smooth fabric of spacetime, which suggests that gravity is the result of the curvature of a continuous, undivided spacetime. At the heart of loop quantum gravity is the idea that spacetime can be described by networks of loops, called spin networks, which represent the fundamental structure of space at the quantum level. These networks are made up of individual links that form a kind of web-like structure, and as the network evolves, it gives rise to the geometry of spacetime. This approach doesn't require a background spacetime, as it is built from the very interactions of the quantum states themselves. One of the key figures in developing loop quantum gravity is Carlo Rovelli, who has helped shape the theory and its potential implications for understanding the fabric of spacetime and the nature of gravity at the quantum scale. In contrast, string theory offers a different approach to reconciling general relativity with quantum mechanics. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings vibrate at different frequencies, and their different vibrational modes correspond to the various particles we observe in nature, such as quarks, electrons, and photons. String theory is a potential theory of everything because it aims to describe all the fundamental forces of nature, including gravity, within a single framework. One of the most intriguing aspects of string theory is that it suggests the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. According to string theory, these extra dimensions are curled up so small that they are not directly observable, but their presence has profound implications for the structure of the universe. String theory also predicts the existence of brains, which are multidimensional objects that can contain entire universes. In this view, our universe might be a 3-dimensional brain embedded in a higher dimensional space. The work of physicists like Edward Witten, a leading proponent of string theory, has helped to push the theory forward, although it remains speculative and lacks direct experimental evidence. String theory's appeal lies in its potential to unify all of physics into a single, elegant framework. However, its complexity and the absence of direct experimental predictions have made it difficult to test, which is one of the reasons it remains a subject of debate among physicists. Both loop quantum gravity and string theory aim to provide a consistent description of quantum gravity, but they take different approaches. Loop quantum gravity focuses on quantizing spacetime itself, whereas string theory introduces higher dimensions and vibrating strings as the fundamental building blocks of the universe. Each approach has its strengths and challenges, and both are still works in progress. The implications of quantum gravity for our understanding of spacetime, black holes, and the early universe are profound. One of the most exciting prospects of quantum gravity is its potential to explain what happens at the singularity of a black hole, where general relativity breaks down. According to general relativity, the singularity is a point of infinite density and curvature, where the laws of physics cease to be useful. However, quantum gravity theories suggest that at the quantum level, space-time may not behave in such a singular, infinite way. Instead, the quantization of space-time could smooth out these infinities and provide a more complete description of what happens near a black hole's core. The early universe presents another challenge for quantum gravity. The conditions that existed just after the Big Bang were incredibly hot and dense, and quantum effects were significant. General relativity cannot fully describe the dynamics of the very early universe, as it doesn't account for the quantum nature of space-time. The unification of general relativity and quantum mechanics is expected to offer insights into the behavior of the universe at the smallest scales, particularly during the moments of cosmic inflation, when the universe expanded exponentially in the first fraction of a second after the Big Bang. Understanding quantum gravity could help physicists unravel the mysteries of the universe's origin, providing a more complete picture of the Big Bang and the forces that shaped the cosmos. One of the key challenges of quantum gravity is that, by its very nature, it deals with scales that are far beyond our current ability to observe directly. The Planck scale, where both quantum mechanics and general relativity become important, is incredibly tiny, about 10 to the minus 35 meters. This is far smaller than the scale at which current experiments, like those at particle accelerators, operate. As a result, much of the research into quantum gravity is theoretical, with scientists looking for ways to test their ideas indirectly. For example, researchers hope that quantum gravity will provide explanations for phenomena like the behavior of black holes, the nature of dark matter and dark energy, and the quantum fluctuations that occurred in the early universe. Experimental research is essential for bridging the gap between quantum mechanics and general relativity. One approach is to look for signatures of quantum gravity in the cosmic microwave background radiation, the afterglow of the Big Bang. By studying the patterns and fluctuations in this radiation, scientists hope to uncover clues about the quantum nature of space-time. Similarly, the study of black holes and gravitational waves might reveal insights into how gravity behaves at quantum scales, potentially providing the experimental evidence needed to support one theory of quantum gravity over another. The search for quantum gravity is not just a scientific endeavour, it's a philosophical one as well. It asks us to reconsider our most fundamental assumptions about the nature of reality. If space-time itself is quantized, what does that mean for our understanding of space and time? If gravity is a quantum force, how does that change our view of the universe's structure and evolution? As scientists work to reconcile the macro world of general relativity with the micro world of quantum mechanics, they are not just seeking a new theory, they are seeking a deeper understanding of the very fabric of reality. Ultimately, the discovery of a unified theory of quantum gravity would be a monumental achievement in science. It could provide the key to understanding the most profound questions in physics, from the nature of black holes to the origins of the universe. It would also force us to confront the fundamental nature of time and space itself, challenging our very understanding of what is real and how the universe works. As we continue to explore these questions, we move closer to unraveling the deepest mysteries of existence and uncovering the true nature of the cosmos. As we explore the vast expanse of space, time, and gravity, we are constantly reminded of the limits of human understanding. While science has taken us further than ever before, answering some of the most profound questions about the nature of the universe, there are still vast stretches of knowledge that remain just beyond our reach. As we strive to understand the deepest mysteries of existence, we are confronted with the realization that there may be fundamental truths about the cosmos that lie forever outside the grasp of human comprehension. Theories in science evolve, often in ways that challenge our intuition and force us to rethink everything we thought we knew. What we now accept as fact, such as Einstein's theory of general relativity or the strange behaviors of quantum mechanics, was once considered revolutionary and even unimaginable. But each breakthrough brings new questions and new theories, and with each answer we find ourselves standing at the edge of yet another mystery. The universe is vast, and the more we uncover, the more we realize just how much is still unexplored. Even as we marvel at the beauty of scientific discovery, we are reminded that there is always more to learn, always more to discover. One of the great thinkers who grappled with the limits of human knowledge was Immanuel Kant, an 18th century philosopher. Kant's work on the nature of space and time was groundbreaking, as he suggested that space and time were not simply properties of the external world, but structures of the human mind itself. According to Kant, we cannot directly know the things in themselves, the world as it truly is, independent of our perceptions. Instead, what we experience as reality is shaped by our senses and our cognitive faculties, which organize the raw data of experience into concepts of space, time, and causality. This philosophical perspective points to a deep truth. Our understanding of the universe is limited by the very nature of our minds and senses. We are, in a sense, confined to experiencing the world through the lens of our own mental frameworks, which may not fully capture the true nature of reality. Kant's ideas resonate with modern scientific theories in profound ways. As we explore concepts like space-time, gravity, and quantum mechanics, we are constantly confronted with the limits of our understanding. For example, our attempts to unify the seemingly incompatible theories of general relativity and quantum mechanics often bump up against the limits of our conceptual frameworks. Just as Kant suggested that we can never truly know the world as it is, we may never be able to fully understand the universe at its most fundamental level. The very nature of space and time may be beyond the reach of human cognition, no matter how advanced our science becomes. This brings us to the role of mystery in scientific progress. Science, at its core, is about curiosity, the drive to uncover the unknown and to understand how the universe works. But the pursuit of knowledge is not a straightforward path. Mystery is a crucial part of the process. Without it, there would be no motivation to explore, no questions to answer, and no discoveries to make. Throughout history, the greatest scientific breakthroughs have come from confronting the unknown, from asking bold questions that seemed impossible to answer. Whether it was the discovery of gravity, the nature of light, or the behavior of subatomic particles, each breakthrough has pushed the boundaries of human understanding, uncovering new mysteries and new frontiers. But mystery also reminds us of our limitations. Even as we push forward, there are questions that may never be answered, aspects of the universe that we may never truly understand. Some scientists, like Albert Einstein, spent their entire lives trying to find a unified theory that would explain both the macroscopic world of general relativity and the microscopic world of quantum mechanics. But even as Einstein's theories revolutionized our understanding of gravity and space-time, they also raised deeper questions about the nature of reality. In many ways, science is an endless process of pushing the boundaries of knowledge, constantly encountering new mysteries, and finding new ways to explore the unknown. Curiosity is the driving force behind scientific discovery, and it is this relentless quest for understanding that has led to the incredible advances of modern physics. But even as we uncover more about the universe, we remain aware of the vast unknowns that still lie ahead. The very act of discovering one thing often opens the door to many more questions. And as we continue to push the limits of our knowledge, we must recognize that some mysteries may remain beyond our reach, whether due to the inherent limitations of human perception or the complexity of the universe itself. As we look toward the future of scientific exploration, we find ourselves in a world where questions about the nature of space, time, and reality are more pressing than ever. From the search for a theory of quantum gravity to the exploration of black holes and the origins of the universe, there are still countless mysteries that await us. And with each discovery, we are reminded of the vastness of the unknown and the limits of our understanding. But it's through curiosity, perseverance, and the willingness to confront the unknown that we continue to expand the boundaries of knowledge. In the end, the search for understanding is not just about finding answers, but about embracing the mystery itself. It is in the pursuit of the unknown that we grow as a species, constantly expanding our horizons and pushing the limits of what we thought was possible. And even as we encounter mysteries that seem beyond our comprehension, we continue to ask the big questions, to seek new ways of thinking, and to explore the infinite depths of the universe. The journey of discovery is ongoing, and the mystery is not a barrier, but an invitation to keep searching, questioning, and exploring. As we continue to push the boundaries of knowledge, we'll see that the search for understanding is not just a scientific endeavor, it's a philosophical one too. Our exploration of the cosmos raises profound questions about the nature of reality, the limits of human perception, and the very meaning of existence. What is real? How do we know it? What are the boundaries of our understanding? And how far can we go in unraveling the mysteries of the universe? These are questions that will continue to shape our quest for knowledge for generations to come as we keep moving forward, guided by curiosity and the drive to understand the vast and mysterious universe that surrounds us. Throughout this exploration of space-time, gravity, time and reality, we've journeyed through the fundamental forces that shape our universe. From Einstein's groundbreaking theories of general relativity, which revolutionized our understanding of gravity, to the strange and paradoxical nature of time in the quantum world, we've seen how the cosmos operates on scales both vast and minuscule. Concepts like space-time curvature, black holes, and the multiverse challenge our perception of reality and stretch the limits of human understanding. Yet, even as science provides us with profound insights, it also leaves us with many questions. How does gravity truly work at the quantum level? What is the true nature of time? Is our perception of reality just one of many in an infinite multiverse? As we continue to uncover the mysteries of the universe, the more we realize how much there still is to explore. The pursuit of knowledge is never complete. Science is always evolving, offering new discoveries and posing new questions. Our understanding of the cosmos is in constant flux, as each answer we uncover opens the door to new, deeper mysteries. And as we seek to understand the nature of space, time, and reality, we are reminded that curiosity and wonder are the driving forces behind all scientific inquiry. As we reflect on the profound nature of time and the universe, let us continue to ask the big questions. Let us embrace the mystery and wonder of the cosmos, knowing that the journey of discovery is far from over. The universe is vast and there is still so much to learn, so much to explore, so much to understand. And it's that very curiosity, that desire to know more, that propels us forward, ever seeking, ever discovering.